this second section of the mechanical properties of materials, we will discuss a very important concept called tensors, because so far you know about the scalars and vectors. For example, when you talk about any simple numerical counting of a system, you talk about the kind of systems which are scalars. But when you talk about something which has a sense of direction, let us say force, one example, then you talk about it in terms of a vector. But when we talk about stress, okay, so we actually would refer to stress not like only one direction associated with it, but if you consider, for example, for a 3-dimensional space, then you have something like 9 components of stress. So, for this kind of a situation, we need a kind of a more generic abstract way of describing the system, and that will be in terms of tensors. Okay. So, that is what we will be doing for both stress as well as for strain. So, this is kind of a generalization first of all on scalars and vectors. Okay. Now, how do we define the tensor for say stresses and strains? Before we say that, we can also show that how scalars and vectors could be special case of tensors, okay, of certain ranks. The rank of a tensor is defined by the number of directions or dimension of the array that is required to describe it. Okay. So, suppose we are talking of an n dimensional space and we are talking of a tensor with r direction or rank r, then it can be represented by c components such that n to the power r equals to c. Now, let us try to use this in terms of our day to day experience. Suppose we talk of a scalar quantity, that means say how many pens, you ask me how many pens do I have in my pocket. Okay. So, suppose if I have one pen in my pocket, then this is a scalar quantity, and this scalar quantity can be considered to be a tensor of rank 0 in a 3-dimensional space. In other words, n is here 3, r is here 0, and hence 3 to the power 0, that is only one component without any sense of direction. The number of pens, that is only the number itself, that is a scalar quantity. Now, suppose we talk about that how do we move from a position A and to a position B. So, now I do not only need the distance to cover, but also I need to say that which direction I will be covering. Okay. Okay. So, for example, you have to go this way and this way, the combination of directions in order to reach this location. So, if you have this kind of a sense of direction, that means you have a magnitude as well as the direction that is associated. So, it is 3 to the power 1 now in a 3-dimensional space, that means you need 3 components, and no wonder that any vector in a 3-dimensional space you always denote it with respect to 3 unit vectors, if you remember, I, j and k. So, that you can actually say that this distance d is nothing but something like x I, y j and z k. Okay. So, that is how you define the vector in terms of the distance, velocities, etc. There are many such things where this first rank of tensor is important. When we will talk about stress, the stress is actually a something which is of rank 2. So, it is a tensor of rank 2, which is also known as a dyad. Okay. So, that means here you need a magnitude as well as 2 directions every time, that means it is 3 square, or in other words 9 components are needed in order to define the stress at a point. Okay. So, that is why I told you earlier that just a very simple generalization of a stress as a force per unit area does not really make a sense, because which area are we talking about? Now, you have a much better definition of stress, that suppose you consider a point and you have you consider a cube all around this point. Okay, that is what we are showing here, right? A cube all around this point, and on that cube, so you have various surfaces on the cube, right? And if you look at it, that you have you need actually 3 normal components, okay, and 6 shear components. So, sigma xx, sigma yy, sigma zz, 3 normal components and 6 shear components. Okay. Why do you need 6 shear? Because there are some shears like sigma xy and sigma yx which are actually same, shear and complementary shears are there. So, you need 3 normal and the 6, to total you need 9 components, okay, in order to define the stress at a point, and that is a tensor of rank 2, that is what is also known as a dyad. Okay. So, thus just like stress is a tensor, a dyad of that is of rank 2 tensor, similarly strain is also exactly the same way tensor of rank 2. So, you need 2 rank 2 tensors to define the stress and the strain. Naturally, if you are talking about modulus of elasticity, then actually you need a rank 4 for in order to define the relationship between the 2 dyads. Okay. Now, there is something more. So, that is about the stress. The other interesting thing is the Poisson's ratio. Okay. This refers to that when I am actually extending a material, let us just take this example that we are extending a material, okay, in one direction. Suppose we are taking the material like a dog bone shape in a universal testing machine, and I am applying the tensile force. Okay. This is a rubber sample, and you can see that how the thickness is reducing in the other direction. Okay. So, this being a rubbery material which has a Poisson's ratio close to 0.5, this shows beautifully that how it is narrowing down in the direction perpendicular to the application of the force. Okay. So, this nature of a material is actually depicted by what we call the Poisson's ratio of the material. So, that is the Poisson's ratio, which is the ratio of the lateral strain to the tensile strain. Now, if a material does not exhibit this behavior, there are some materials which does not exhibit this behavior. For example, a bottle, cork of a bottle, they generally neither expand in terms of when you are compressing it, or nor the other way around. So, they have a Poisson's ratio which is close to 0. In fact, cork's Poisson's ratio is nearly close to 0. Most of the other materials in the day to day experience that you use, for example, the metals, they have a Poisson's ratio between 0.25 to 0.3, etc. Okay. Concrete has a Poisson's ratio of 0.2, and rubber has a Poisson's ratio as I have just now shown you, and that has a Poisson's ratio close to 0.5. Can a material have a negative Poisson's ratio? That means, when we are actually contracting the material or expanding the material, let us say just like that rubber experience, when I am expanding the material, instead of contracting, can it expand on the other direction? Yes, in certain cases it can. Let me just show it to you through an example. Now, this is actually a kind of a re-entrant honeycomb structure. This is a auxetic structure. So, in this auxetic structure, if you look at it, that it is each of the honeycombs, instead of the honeycomb with a positive angle, they are having a negative angle, each one of them. And these, what happens in such a case? Suppose now I am trying to expand the material. So, I am expanding it in this direction. You see that the other direction, that is in the perpendicular direction, instead of contracting, it is actually expanding. The more these reentrance angles are actually unfolding, it is expanding more and more. So, and the other way, when I am compressing, you can see other directions, instead of expanding, it is also getting contracted in the other direction. So, expansion is creating expansion, compression is creating compression. That is the beauty of an auxetic structure, of a structure which is having a negative Poisson's ratio. So, we have talked about various types of Poisson's ratios, okay, and that definitely is a very important consideration, a material property consideration when we are actually selecting a material. Now, we also have talked about stress and strain. The stress and strain are related by something which is known as the Hooke's law. Okay. So, there are of course, the Hooke's law which actually can be considered as a relationship between a single stress factor and a single strain, or in a generic sense between a stress tensor and a strain tensor. Okay. So, in that case, if I consider the relationship to be a matrix relationship, that means sigma I j, okay, equals to, in that case it will be E I j k L epsilon k L. Okay. So, that is the most generic Hooke's law. So, basically Hooke's law is something which is relating between the stress and strain, and each stress and strain component within a linear elastic domain is generally found out to be having a proportionality. That means, if you increase the stress 2 times, the strain also will increase 2 times. So, there is a sense of proportionality that will be there between the two. Okay. So, that is the simplest form of the Hooke's law, which we also call, we also refer that if we do it for a component, then this actually the E becomes what we say as the Young's modulus, named after one of the most famous physicist and physician, Sir Thomas Young, who had first made very important notes on elastic behavior of materials. Now, the way a normal stress component is proportional to a strain component and related by Young's modulus. Similarly, if you have a shear stress component, that will be proportional to shear strain, and there the modulus of elasticity is referred as shear modulus or G. And if you remember the case of that hydrostatic pressure case, there actually it is not happening the change in a direction, but in terms of a volume change. So, you consider it for any fluidic case. So, that is why the negative sign is actually introduced here, because the positive pressure causes a shrinkage of volume. So, here you get the volume change as the volumetric strain, and that is related with the hydrostatic pressure, and hence the modulus here is known as the bulk modulus. So, we have 3 different modulus. Okay. The elastic modulus in the first case, which is Young's modulus, shear modulus and bulk modulus. All 3 modulus, however, have the same unit in terms of the unit of the stress, because the strain is unitless. So, it has the same unit as the unit of the stress. Okay. So, that is about the Hooke's law. Now, and which correlates between the stress and the strain, and you can get actually the elastic modulus of the system. The point is that this elastic modulus varies, and this is a measure of actually the stiffness of the system. Okay. The way very easily I worked with a rubber sample, with a steel sample if you give me, I may not be able to work so easily. So, it has a higher stiffness, that means a higher modulus of elasticity. Now, this is depicted in a beautiful chart from actually Ashby and Jones, and that gives the elastic modulus for different groups or types of materials. For example, if you consider ceramics, they have generally a very high elastic modulus like diamond, and then they may have some some of the things which may have lower modulus of elasticity, something like say for example, the glasses or the ice or the graphite, okay, the cement, they may have somewhat lower modulus of elasticity, but in general ceramics have reasonably high modulus of elasticity. If you look at the metals, there are some metals which shows quite high modulus of elasticity. For example, tungsten is one of them, chromium is another of them. No matter, that is why for the making the super alloys, this kind of materials are used, because they deform much less with the same application of force. And then where is so iron and steel is here, for example 200 gigapascal kind of a thing, and then much softer ones are, for example aluminum or zinc or tin, magnesium. They are much softer in terms of the metals. Now, if you look at the polymers, you can see that there is nothing here. That means the polymers are a degree, several orders of magnitude lower in terms of the stiffness, and there something like, that is why I told you that about 2 gigapascal is something maximum that we generally observe, and there in the higher range you get something like polymethyl methacrylate, polystyrene, nylons, etc. And those which are very low are something like foamed polymers, PVCs, rubbers, etc. They show very low modulus of elasticity, or in other words the compliance is very high in such materials. Then if you look at the composites, the natural composites are generally softer, something like woods, etc. But the man-made synthetic composites actually have modulus of elasticity which is comparable with the metals, CFRPs, fiberglasses, etc. So that is why composites are replacing the metals wherever the high stiffness is required. So, so that is kind of a comparison chart which you can keep in your mind. In terms of the absolute values here, once again I have given 3 values we have given from Callister here, and just for reference, for example, if you consider aluminum, approximately 70 gigapascal modulus of elasticity, shear modulus is approximately 25, and Poisson ratio is approximately 0.3. Okay. So, again in this list you would see that a high modulus of elasticity you are finding in something like tungsten, okay, and the shear modulus is also high in that same range, but shear modulus is usually always lower in comparison to the Young's modulus of the system. What does it mean? It means that you can actually shear the material or twist the material, deform the material in the shearing mode much easily instead of actually elongating or compressing the material. Okay. And the Poisson ratio you can see is not really varying, it is more or less in a range of something like 0.3, around that range, okay, for most of the metals. So, this is just for a comparison of these properties in various metals. Now, we carry out how do we measure this property. In order to measure this property, we use a tensile testing system, okay, in a machine which is known as actually universal testing machine, in which we find out properties like for example ultimate tensile strength, yield strength, okay, percentage elongation, Young's modulus of elasticity, etc. Okay. So, I have just now shown you that in a UTM machine how we are we can deform the rubber specimen, the same specimen that I have shown you, okay, can be used in this case. Universal testing machine is a beautiful machine where you can actually load a sample in various ways, tension, compression, shear. Not only that, the loading can be made dynamic loading and which can include things like fatigue, etc. So, that is how do we generally carry out this universal testing machine, the tensile testing. Okay. Now, if you carry out such testing of a ductile metal, okay, how would you find out the stress strain diagram? And that is the the engineering stress strain diagram of the material. How do you usually see the stress strain diagram? If you look at it, that the stress strain diagram shows certain features, but please keep in mind that this is for a ductile metal. Okay. So, you will see that there is an initial region where the material, if you actually unload the material, it will come back to the same point itself, and that is known as the elastic limit. Okay. That means the maximum stress that it can withstand without any measurable permanent strain after unloading. Now, in the elastic limit, of course, there are two regions. In one region, up to some region, it is actually perfectly linear, and beyond that it is slightly nonlinear, but still if you release in the nonlinear region, it will come back to its original position. That is what is the defines the elastic limit. Now, then the point comes here, that is the yield strength point. Beyond the yield strength point, if you actually deform the material, then it will start to deform plastically. So, what it means is that beyond that point, if you actually start to unload, there will be some amount of deformation which will always remain into the system, and that is why the yield strength position is very important, because that says the onslaught of actually plastic deformation in the system. Okay. So, as I am increasing the load, I am going beyond the yield strength level, and I am actually watching the uniform plastic deformation. Now, if I increase the load further, what is going to happen is something like a necking phenomena that would start to happen, okay, and then the material will go to the fracture. Okay. So, that is what generally happens for a ductile material. So, in that, beyond that necking point, what you get is a non-uniform plastic deformation. So, the plastic strain itself can be divided into two parts. One is the when it is uniform plastic deformation, okay, that is the first part, and then when there is a non-uniform plastic deformation till failure. Okay. So, that is what we will find into the system. And what is the point that is important for us is that up to the necking, we get actually the ultimate tensile strength. So, that is the maximum load divided by the original cross sectional area of the system, that gives us the ultimate tensile strength. Okay. Beyond that, you would not expect a strength of the material, because beyond that, if you take the force, it is actually going to take us towards the fracture. That is why ultimate tensile strength plays a very important role in terms of the product design. And also the other two important factor is that what is the percentage elongation, that is the ratio of the difference of final to initial length change over the initial length, and similarly for the area. So, that actually tells us that how compliant is the material. So, this is a typical stress strain curve for a ductile material. How will it look like for a brittle material? Okay, I can just in a very small qualitative manner we can draw it here, that suppose the stress is denoted by sigma and strain by epsilon. So, if I draw the sigma epsilon, for a brittle material it is just one single line, okay, and maybe some point of nonlinearity, but that is it, and then it sharply fails. That means, it will not show any plastic strain, any plastic deformation. Okay. That is generally happens in terms of the brittle material. The other important point here is that generally the yield strength, if you do not find a very sharp point where this this is happening, we consider approximately this 0.002 level, that means the 2% strain level. We find out that where it is intersecting, and that point is defined as the yield strength level, because that is generally the strain level which it can take in general in metals without any permanent deformation. But this is very specific to the metals. For the things like elastomers or rubbers, this can become something like 5% to 10%. Okay. So, depending on the material, this position may change. Now, then if we actually consider, however, the true stress strain curve, that means if we consider that the area is actually changing, if you look at it, that as you are deforming, this area is actually changing, this area is becoming smaller and smaller, the neck formation is happening. So, the area is changing, and if you consider that actual area, you will see that it is not actually, the stress strain curve is not drooping, but it is actually increasing, and it is increasing because even if the the force you are increasing, the area is actually decreasing at a very rapid rate. So, that is why the or the true stress actually is increasing at a very rapid rate. Now, in the uniform plastic deformation, the stress strain relationship is actually governed by a power law, which is like sigma t is k times epsilon t to the power n, where this n is 0 for perfectly plastic solid, n is 1 for elastic solid, okay, and for most metals it will be in the plastic region between 0.1 to 0.5. So, that is how it would behave in the true stress strain curve, okay, which we generally overlook. Actually, we only look at the stress strain curve that comes after the UTM machine. So, the true stress strain curve, actually true stress is denoted by this relationship, which is something like the sigma t as sigma times 1 plus epsilon, and the true strain epsilon t is log of 1 plus epsilon. Okay. And the relationship between engineering strain and true strain is governed by this relationship. So, this is what you can just very simply mathematically you can actually obtain this relationship. Now, the other point is that the materials based on these stress strain relationships are actually divided into sub categories, like the homogeneous materials, for which the properties are actually independent of where I am measuring the property. That means, here you get a property and here you get a property, all the directions, if you look at it, you are going to find the same modulus of elasticity, but it varies from direction to direction. In one direction it is E1, in another direction is E2. So, that is what is a homogeneous material, where at different points you get the same pattern of modulus of elasticity. For isotropic, it is actually direction independent. You get this at a particular point, if you consider, you get E1 in all the directions. But if it is not homogeneous, then at a different point you get E2 in all the directions, and E1 and E2 are not the same. They are not the same. If they are same, then they will become a homogeneous and isotropic material. And if we consider an orthotropic material, in that case it is slightly different. In that case, you will see that at different points it is homogeneous, but the modulus of elasticity varies in different directions, in the sense it varies in 3 different mutually orthogonal directions, that will be E1, E2 and E3. This is for generic general orthotropic material, but for specially orthotropic material you may disregard one of them and it only varies in one set. That means, something like E2 and E3 will vary, okay, but E1 may remain the same. So, that is what happens for spatially orthotropic material. Spatially orthotropic. This is typically a case like if you consider a laminated composite, then each lamina, which is very thin in one direction, are actually considered to be spatially orthotropic material. So, that is a very special case of a general orthotropic material. Now, the relationship, the elastic constants are actually related with each other by the relationships which is shown here, that the E is related to G and G is related to K, okay, and hence if you know actually for a linearly elastic, isotropic and homogeneous material, you need only 2 elastic constants, and then the other 2, that means we have these 4 K, nu, E and G. Out of them, any 2 if you give me, I should be able to derive the other 2, provided the material is linearly elastic, isotropic and homogeneous material. However, in case of anisotropic material, there are 21 independent elastic constants. Okay. So, it is a much higher in terms of the variations. And if it is orthotropic material, then it has 9 independent elastic constants that will come into the picture. So, naturally the tailoring is much more for an orthotropic material. Now, that is the relationship in terms of the actually the isotropic and orthotropic and anisotropic materials. So, that is about the stress strain relationship. There are some other mechanical properties which are also important. One of them is ductility. I already talked about it, that it is the how much is the capacity of how much you can draw a material under the tensile stress, okay, and that is very important. And there is something that you will also see in terms of ductility, which is known as the ductile failure, the telltale sign of the neck formation of the system, and the brittleness of a system. So, the difference between a brittle and a ductile system, I have already drawn the stress strain curve for a brittle system, and a ductile system is that precisely this ray, the presence of this plastic strain that is there for a ductile material, and that is absent for a brittle material. So, that is very important point that we have to keep in our mind while comparing between various material properties. Now, the other important point here is actually the resilience of a material, which is the capacity of a material to absorb the energy, okay, elastically. So, it is in the elastic domain. When it is deformed elastically, how much of energy you can absorb, and if you consider the stress strain diagram, and if you consider the area under the stress strain diagram, you can actually find out that this is something like sigma y square over 2e in a kind of an approximate measure, and that is, so that means if you know what is the yield stress and if you know what is the modulus of elasticity, you can actually compute that what is the resilience of the material in terms of modulus of resilience and how much of energy the material can absorb, which is very important in applications like spring type of applications. So, the resilience is another important mechanical property. The last important property in this direction is the toughness. Toughness is also the area under the stress strain curve, just like the earlier case, but here you are considering the plastic region also. Okay. So, earlier you are confining yourself within the elastic region, now you are considering the plastic region also. In fact, the test that is very much important towards this direction are actually Izod and Charpy impact test. So, this is an Izod impact test, where actually you support the sample from one position here, you are supporting the sample and you are hitting it through a pendulum, and if there is no sample, then it can go to a particular distance. If there is a sample there, then some energy is actually taken by it. So, it cannot go up to that distance. So, you take that ratio of the two, the return ratio you call it, and then that gives a measure of how much of energy is actually absorbed by the material, and which is a measure of the toughness of the material. Now, similarly, there is another very similar test actually, which is known as the Charpy test. Now, the difference between the two tests, the Izod test and the Charpy test, is that in the Izod test you have for example, if I go to the last case, you have the crack, which is you make a notch actually, and the notch actually faces the hammer. So, the hammer faces the notch, So, you are in terms of Charpy, as you can see, on the other hand, the notch is at the opposite side of the hammer. So, that is one of the difference between the two, and also in case of a Charpy test, you are supporting the material at two places instead of at one location. But both of them are very good tests which can measure that how much of energy a material can absorb, and that means how tough the material is, and that actually means that how much is the impact strength that is there in the material. So, here is some kind of a comparison of from the Ashby's table, and as you can see here, if you look at it very closely, that the metals are topping in the list actually, because they can absorb quite a good amount of impact energy, and in fact plastics, even though they deform more, they cannot absorb that much of energy. Brittle materials of course are the worst here. So, that is what is in terms of the 3 different groups of materials, and composites are somewhere in between. Now, the factors that are important in terms of the impact energy is that for a given material, the impact energy will decrease if the yield strength is increased. So, that is generally found in a material, and the notch serves as a stress concentration zone. So, some materials are more sensitive to notches, and the most of the impact energy is actually absorbed during the plastic deformation of the material. Also, temperature and ductility plays a very important role on it. So, this is where we are going to close this lecture, and in the next lecture we will talk about a few more mechanical properties, that is the hardness of the system, the creep of the system, and the damping.